Thank you for the kind introduction and welcome from my side as well. During the course of the next few minutes, we are going to introduce you to the core idea of our work, and you will learn how you can leverage existing domain knowledge in programs to generate complex fuzzing inputs for target applications. But before we talk about the core idea, I want to talk about how fuzzing works and what are the current problems in the research field are. So let's first have a look at a typical fuzzer setup. We have a target application. In this case, this is unzip. And we are providing this target application with some input, which are zip files typically. So we are using first, or we're choosing for first a zip file, and we are mutating it somehow by, for example, flipping a bit. And then we are providing this mutated file to the target application. And then we are using typically some fuzzing as some feedback metric. In most cases, we are using coverage because code that is not covered cannot be we cannot detect bugs in code that is not covered. So if we are increasing or maximizing the code coverage, we are also increasing the likelihood of finding bugs. While this works pretty well for easy to fuzz targets like programs that parsing binary input, it gets much harder if we have hard constraints such as magic values, CRC checksums, or even encryption and signatures. Because if you are mutating a signature, like flipping a bit in a signature, it gets invalid and you have no chance to repair it by flipping more bits, for example. And to overcome these problems, we have multiple approaches. And two of the most widely known ones are, the first one is taint tracking. So we have, for example, a magic value, which is compared against some input value during the program execution. And we have to find out this magic value in order to overcome this compare instruction in the target application. And for this to get easier, we are using taint tracking. And taint tracking allows us to find out which bits in the input file has influence on the compare instruction we are currently targeting. And therefore, we can ask the taint tracking engine to give us these bits or tell us which bits are interesting in the input. And we can concentrate our mutation efforts on these bits and therefore increase the likelihood of solving the constraint by flipping the bits. If this is not enough, we can use a symbolic execution. So for example, if we have a CRC checksum, which is compared against a CRC checksum that was computed over the input file, we can use symbolic execution to formalize the current program state, to use symbolic execution to generate a concrete input out of this formula. So we can basically ask the symbolic execution engine to produce a valid input file that will overcome this check in the program. While this is really powerful, it fails in some instances. So for example, if we have cryptographic hashes or encryption, we are not able to use symbolic execution to deduce a correctly encrypted input from the program state, for example, because it's infeasible to compute such things. And what's interesting about these both approaches is that they both rely on extracting domain knowledge from the target application. So they try to infer how the data flows in the target application, or they even try to formalize the domain knowledge in the target application by using symbolic execution. And based on this observation, we had the idea to use instead domain knowledge that is existing already in programs, and therefore we are replacing the normal fuzzing engine with the second program we call the generator. And the generator is, in this case, zip, because we are targeting the program unzip, and zip is able to produce perfectly valid inputs for the target application. And if we are now providing input to the zip application, we can execute the application, and we are getting a perfectly valid zip file, and this zip file can then be presented to the target application. As you may already have noted, is that we currently have no control over the process in regards to injecting mutations or something like that, what we typically do in fuzzing. And to overcome this problem, we are mutating the program itself. So during processing of the input, we are mutating the zip program, and all the instructions that are executed and are participating in the process of converting the input into the output are possible targets for fault injection or mutation. And in our approach, we are injecting faults in load and store instructions. So instructions that are working with memory. And we are applying bit mask values to, for example, a value that is read from memory or written. And therefore, we can introduce mutations in the process, and we are getting a mutated output if we targeted the correct instruction that had actually influence on the target on the generator's output. And in the final step, we can then use this mutated file to use it as fuzzing input for the consumer. And we are using, again, coverage feedback to decide whether the mutation we applied to the generator was meaningful or not. And if we found out that we had injected a fault that caused some interesting mutation in the zip file and also caused new coverage in the consumer, we know that we can keep this mutation and use it for further iterations during fuzzing. And since since we can inject faults at an arbitrary place, we can even inject faults before hard constraints are applied to the output or to the input file format for the consumer. So if the consumer would consume an encrypted zip file and we are mutating an instruction that is executed before the actual zip file is encrypted and stored to disk, we can even mutate the content that is stored in the zip archive. And that is not limited to encryption. We can even use this to mutate data that is later signed during execution, but if we are injecting the fault before the actual signing happens, we can even produce fuzzing inputs that are validly signed. The problem here, or one disadvantage is here that we are executing two applications, so it's a little bit smaller than executing just one as normal fuzzing setups. And therefore, we are combining this approach with AFL++. So we are using our approach or our prototype Fuzztruction to generate high-quality seeds, and we are passing this high-quality seeds to AFL++, so AFL can apply typical bit mutations to increase the coverage even further. And now to see whether this approach works, we also conducted an evaluation where we targeted 10 different program pairs, and we used different targets that had different roadblocks. So for example, we had optdump, which most works evaluate against, which doesn't embed any checksums or cryptographic primitives, but we also used gen-ASR or ASR, which are both subcommands from OpenSSL, which use ASR keys and therefore cannot be fuzzed by typical fuzzers. And in the two of the targets I want to talk about in specific. The first one here is PNG to PNG, which is the binary that comes alongside libPNG, and what it does is reads a PNG file from disk, parse it into some memory representation, and then store it back to disk. And during this process, we are mutating the PNG to PNG program, and therefore we are getting mutated output. And this mutated output is pretty interesting because PNG files typically embed CRC checksums, which are normally hard to fuzz or normally hard to generate by off-the-shelf fuzzers. And if we are looking at the results, we can see two things. The first thing here is that we are outperforming the competitors, and the second thing is that we have here a fuzzer that is called SimCC, which is actually backed by a symbolic execution engine, and we are still better in terms of coverage to generate better inputs than a symbolic execution engine, which is pretty interesting. And the second thing that we can see here is that there is Fuzztruction no AFL, which is our approach without combining it with AFL. And it looks like it is covering the same amount of basic blocks as AFL++ does. But during our evaluation, we saw that it's actually a disjoint set of basic blocks. So we are finding with Fuzztruction other things than AFL++ typically do. And we can also see this by the great synergy effects between AFL++ and Fuzztruction, as we can see in the top line. And the second target I want to talk about is 7-zip. And here we are using 7-zip in compress mode and instruct it to encrypt the input, and we are getting therefore an encrypted zip archive that we can then present or then pass to 7-zip. And if we are looking at the results, we can see two interesting things. The first thing is we are outperforming the related work, and we can also see that SimCC is missing, which is pretty interesting because SimCC failed to compile the target application. And this is a good showcase, in my opinion, that it's still hard to apply symbolic execution engine to real-world applications. And this brings me to the takeaways. So what we learned here is that we can leverage existing domain knowledge in generator programs, and by mutating these generator programs, we are able to produce complex fuzzing inputs that are basically only limited by the capabilities of the generator program itself. And we can use this approach to solve complex constraints such as encryption or even signatures without relying on any heavyweight program analysis techniques. And with that being said, thank you for your attention, and I'm now open to questions.